Greetings, dear students! This video is part of the Liquid Propellant Rocket Engine Tests course from the Department of Aircraft Engine Theory at Samara University. In this course, you will learn why tests are conducted, how to organize them, what tools are needed to conduct them successfully and safely, how to process experimental results to get the most accurate information, how to get the desired result with the minimum number of tests, and much more. This is the third video, the third part of the course. In it, I'll tell you how the results are processed. The elements of the mathematical theory of random errors are used to estimate the error in the measurement. The law of the random error distribution is derived from the following assumptions. Measurement errors take on a continuous series of values. For a large number of measurements, errors of the same magnitude but of different signs occur with equal frequency. Large errors are less frequent than small errors. These assumptions, called Gauss postulates and verified by numerous experiments, lead to what is known as the law of normal error distribution, or Gauss's law, where phi is probability density, x measured value, this is expected value, sigma is standard deviation, and this is measurement dispersion, a parameter describing the magnitude of random errors. Other random error distributions are available, but in most cases, where measurement errors are not too large, a Gauss law is an excellent agreement with experiment. The figure to the right shows a probability density plot. The value of the shaded area is equal to the probability of a measurement result occurring between x and x plus dx. The total area under the curve, or the probability of a measurement result occurring between minus infinity and plus infinity, is 1. The value of x at which the probability density is at its maximum is called the mathematical expectation. The maximum of the probability density function decreases as the standard deviation increases. Since the area under the curve is always 1, increasing the standard deviation will cause the curve to stretch along the x-axis, as shown in the figure to the left. So, the greater the dispersion of or standard deviation of a random value, the less accurate the measurement. Estimating the random error requires specifying two values, the confidence interval and the confidence probability. Confidence probability is the probability of finding the result of an experiment within this range, and the range itself is called the confidence interval. To find the confidence probability, one uses a Gauss law transformed by substituting a quantile of the normal distribution, and obtain these. The integral on the right is called the probability integral or Laplace function. It is solved numerically because it is not expressed analytically. The confidence probability of a random value within the confidence interval for different values of the quantile of normal distribution is shown and given below. This means that for a normal distribution quantile of 3 out of 1,000 measurements, 997 will fit within the interval from x minus 3 sigma to x plus 3 sigma, and only in 3 cases larger random errors can be expected. Thus, it can be stated that the measurement error of the value doesn't exceed 3 standard deviations. Before testing, a decision is made about the level of measurement reliability, the measure of which is the confidence probability. The more demanding the test, the higher the confidence probability is assigned. If the confidence interval, meaning the measurement error, is too high, efforts are made to increase the accuracy of the measurement, increase the number of measurements, use of more accurate instruments, etc. Up to now, we have assumed that we have an unlimited number of measurements at our disposal. In practice, however, we often have to deal with a finite number of measurements. In this case, the formula shown on the left-hand slide should be used to estimate the error in the arithmetic mean value of all measurements taken. As the number of measurements increases, the standard deviation of the arithmetic mean decreases, which is often used to improve accuracy when random error is a determining factor. To assess the accuracy of the measurement method used, you can apply the formula for calculating the standard deviation of an individual measurement, shown on the slide on the right. Knowing this, you can select the number of measurements required to obtain the acceptable random error of the final measurement result. When the number of measurement n is less than 20, the relation between the confidence probability and the interval is determined not only by the standard deviation, but also by the number of measurements, because the value of the standard deviation of the arithmetic mean is itself affected by the error depending on the number of measurements. An appropriate function is derived by Gauss under the pseudonym student. And this value, called the quantile of the student, is given in appropriate tables. An example of such a table is shown on the slide. This allows for a given level of reliability P for n measurements to estimate the confidence interval by first calculating the standard deviation. The inverse problem can also be solved. A few words about identifying outliers. An outlier is the result of rough experimental error that violates the regular deviation of a random value from the mathematical expectation. Hence, the probability of its occurrence is small. In practice, all results with an error greater than 3 sigma are sometimes rejected. However, with a large number of measurements, the probability of such errors is rather high. In order to relate the probability of an outlier occurring to the number of measurements, the deviation of the suspected result x from the most likely, or in other words, the arithmetic mean, is calculated and related to the standard deviation. This value is then compared to one of the criteria. If the calculated value is greater than or equal to the table value of the criterion calculated for a particular number of measurements, the result is considered to be an outlier and is discarded. When the number of measurements is less than 10, the Chauvenet criterion is used. Formula and tabulated values are shown on the slide on the left. The Romanovsky criterion is used to detect outliers when the number of measurements is less than 20. Formula and tabulated values are shown on the slide on the right. When calculating the total error of a direct multiple measurement result, both the random error component of the measurement result and the non-excluded systematic errors must be taken into account. Processing the results of direct multiple measurements of a physical quantity x made n times under the same conditions consists of 3 steps. The first step is to determine the confidence interval of the random component of the error in the measurement result. To do this, we need to exclude known systematic errors from the measurement results, to find the arithmetic mean value of the measurement results, which is taken as the measurement results, where x is the ith measurement result and n is the number of measurements. To find the absolute errors in the results of measurements of a physical quantity. To determine the standard deviation of an individual measurement. To identify and discard outliers using the Romanovsky criterion. To calculate the standard deviation of the measurement result. To calculate the random component of the error in the measurement result for a reliability of 95% using the student quantile. The second step is to determine the confidence interval of the non-excluded systematic error in the measurement result. If a systematic error cannot be determined and cannot be excluded by the corrections, such systematic errors are called non-excluded errors. The limits of the permissible main and additional errors of the measuring instruments, as well as the methodological errors and other errors, shall be taken as a non-excluded systematic error. When summing up the non-excluded systematic errors, they are treated as random values with a uniform distribution. The confidence interval of the non-excluded systematic error of the measurement result is calculated according to the formula, where k is a coefficient determined by the confidence probability accepted. In current work, the jth non-excluded systematic error is calculated as follows, where this is the relative error expressed in %. The confidence probability for calculating the limits interval of the non-excluded systematic error shall be the same as that for calculating the confidence boundaries of the random error of the measurement result. The third step is to determine the confidence interval of the error in the measurement result. The total error of the measurement result is calculated using the formula, where k is the coefficient depending on the ratio of random to systematic error and determined by the empirical formula, where s is total standard deviation of the measurement result calculated according to this formula, and where s is this. The results of the direct repeated measurements are presented as follows, where this is measurement result, this one is error of measurement result, and P is accepted confidence probability. The numerical value of the measurement result must end with a digit in the same place as the error value. The following rounding rules apply when processing the measurement results. The accuracy of the measurement results and the accuracy of the calculations in processing the measurement result must be coordinated with the required accuracy of the resulting estimate of the measured quantity. The error of the measured value should be expressed by no more than 2 significant digits. More than 2 significant digits in the error of evaluation of the measured value are retained in the case of precise measurements if the first significant digit is not more than 3. The number of digits in the intermediate calculations when processing the measurement results must be 2 more than the final result. The error in the intermediate calculations must be expressed by no more than 3 significant digits. Rounding of the error value of the measured quantity is done according to the usual rules of mathematics. In tests, it is often necessary to process the results of indirect measurements. For example, let an indirect measurement of y be related to m direct measurements by a known relationship, each of them carried out n times. Obviously, m errors, for example of the first measurement, will cause a certain error in the indirect measurement delta y. Usually the values of delta x are very small and the direct measurements of x can be considered independent. Then the relationship between the direct and the indirect errors n of the measurement, when the indirect measurement is the sum or difference of the direct measurement, is defined by the expression for the total differential of a function of several variables. After transformation and processing, we obtain the following expression, where on the left-hand side we get the square of the mean standard deviation n of the indirect measurement, and on the right-hand side we get the corresponding parameters of the direct measurement. Consider the case where the indirect measurement is the product of quotient of the direct measurement. For example, when determining the density of the substance of a cylinder. Let's find the corresponding derivatives. Convert the following expression into this, where deltas are relative errors of direct measurement of mass, cylinder diameter and height. Thus, if the indirect measurement is the quotient and the product of the direct measurement, then the squares of the relative errors, rather than the mean standard deviations, must be added up, the coefficient before the relative error being equal to the exponent of the corresponding direct measurement. Having completed the measurement experiment, the researcher usually has the results in the form of a printout, protocol or table with numerical data, the errors of which are then determined using the techniques discussed above. Further processing of the results of the experiment consists in finding the functional relationship that links the measured quantities. If measurements have been made for production purposes, such dependencies are used in the product quality analysis to develop appropriate corrective actions. In research and development, the relationship between physical quantities may be necessary for further theoretical investigation of the phenomenon or process. If we plot the experimental points on a certain scale, the problem can be formulated as follows. Find a function such that all the experimental points are as close as possible to the curve that graphically represents the function. The problem is greatly simplified if the type of dependence to be found is known beforehand. For example, let this relationship be, for theoretical reasons, directly proportional to this. The solution then comes down to finding the value of the coefficient a in the expression so that all quantities of the type are minimal. Here z and x are values obtained from the experiment, and z from x the value obtained by substituting x to formula. If the type of relationship between the quantities under study is not known beforehand, it can be picked up by presenting the results of the experiment in different functional scales. To a large extent, this depends on the intuition of the researcher, but there are also some practical techniques. Finally, if a sufficiently simple functional relationship between the quantities cannot be found, the experimental results can also be approximated by a polynomial of more or less high degree, the coefficients of which can be found by various methods. The problem of approximating experimental data is most completely solved by the least squares method. The larger the number of measurements, the smaller the approximation error. It should be kept in mind that when processing experimental data, there is no point in increasing the accuracy of the approximation too much. A reasonable limit corresponds to the error of the experiment. In practice, it is usually limited to the fourth power polynomial. I would like to conclude today's lecture with this. In it you have learned what is error, how to minimize error in direct measurement, how to find the error of a complex quantity. I hope you have enjoyed this lecture. If you still have questions, comments or find errors, don't hesitate to let us know in comments or private messages, and we will meet you in the next video lecture.